Now we have two more talks. The first of these is about planetary materials and their response to tidal deformation, and giving this talk will be Professor Christine McCarthy. Christine is a Lamont Assistant Research Professor at the Lamont Doherty Earth Observatory, operated by Columbia University. She co-runs the Rock Mechanics Lab there, where she conducts laboratory studies that are aimed at understanding the way microscopic properties control macroscopic behavior. And she'll be talking to us about that right now.
Great. Thank you. Alrighty. So this is a little bit of an outline of what I'll be covering today, but by no means am I giving each one of these equal measure. Definitely, probably everyone in this room is far more sophisticated in their thoughts in thinking about big interior, big bodies, and how they behave, their dynamics. So I'm going to be mainly just to provide the context for what I'm really comfortable and strong in. I will kind of start with some of that, but I'm really going to be focusing for the most part on how materials deform. I've worked for a long time as an experimentalist, working on a variety of earth and planetary materials. In particular, I think about kind of from a material science standpoint, and thinking about at the sort of grain and defect scale. And so we'll be talking about that and how different materials deform, but also about I'll tell you we'll get under the hood a little bit on the laboratory experiments and how they're done and how we get the kind of values that hopefully this week we'll be able to manipulate and work with and try to understand how these icy and rocky worlds are behaving. And so by way of that, I'm going to only briefly talk about the interior structures of various bodies. Of course, pressure increases with depth by rho GH, the gravity of the body and the density and how high the material is above you. And on Earth, we've got some exterior constraints. We can look at actual rocks that have been exhumed, or we can use seismology to constrain also thermal gradients. And on other bodies, we can't necessarily do that. I have probably never spent more than 5 minutes thinking about Io, so I'm really excited about being here this week to learn a lot more about it. So I don't know what the current thinking is about the interior of Io, but certainly we've got a really high thermal contrast, thermal gradient, and I think the belief is that there's peridotite, which is dominated by olivine. We can compare this to, for instance, icy satellites, where I usually think about mostly the deformation in this icy outer layer, and we've got pressure gradients and temperature gradients, and of course those temperature gradients are always influenced by convection and internal heating processes, and that's what we're working on this week. Those temperature and pressure gradients with depth, of course, affect the material behavior. So, and this depends a lot on the mineral itself. What is the dominant mineral at different, with depth on these different bodies, and the temperature and pressure profiles. And so we can constrain these based on laboratory experiments, these strength envelopes, how the strength of these minerals with depth. And here, for instance, is comparison of Earth versus one prepared for ice, for Europa. And there are a lot of similarities. In particular, you see like at shallow features, at their shallow depths, we have this brittle response. So we would use, it's dominated by the Byerle's rule, which you determine through friction experiments, and then and that increases as pressure increases with depth. But at some point, temperature becomes high enough to constrain the ductile deformation, and so with depth, it's dominated. Deformation is dominated by viscosity, viscous deformation behavior. And again, these are steady state behaviors here, and we would determine this through creep experiments that we would perform on various minerals. And we see a lot of similarity in the response, but huge variations in strength, of course, and that's dependent on the material. But I'm not going to spend this entire talk contrasting rock and ice, because in my opinion, we don't have to do that. They are polycrystalline materials, and we can compare them to one another by thinking about the homologous temperature. So if you compare materials based on their melting temperature, and you're comparing, say, their behavior at 60% of melting or something like that, then you can start talking just about materials. Polycrystalline materials is what I'll be talking about for the rest of this talk. And of course, there are small nuances and things like that that we can think about when you're coming up with rates and actual magnitudes. But in general, let's talk about polycrystalline materials. Yeah, so for instance, when I'm talking about friction results to people thinking about earthquakes on Earth, we're down here in low homologous temperature space. But when we're talking about in the Earth's mantle, or in Io's mantle, or in an icy satellite, we're talking about homologous temperature in this space. So we're really going to be thinking about this. And that kind of skips something I wanted to talk about here. And that is, although in the brittle regime, there might be some heat production. So what I'm talking about is, if you imagine a pre-existing fault that is being loaded by tides, you could have frictional heating, and the magnitude of that would depend on the velocity of the sliding and the frictional coefficient, and this would increase with normal stress, with depth. You could have some localized frictional heating, and it may be that in order to kind of be able to describe some of the lateral variations that we're seeing on the surface, maybe you will need to invoke those and add those to your energy budget. But for the majority of what we're thinking about, if we're thinking about these whole bodies, I'm really focusing what's happening here in the ductal region. And so I won't really be talking about localized frictional heating. I'll be talking about tidal heating and down in that regime. I want to make sure to clarify that. And Francis was talking about how he wants you to kind of imagine yourself on the surface when you're thinking about how the tides affect the body. And so now I'm asking you to instead think deep inside, go into the interior of a crust or into the mantle, and imagine you're right there at a little cube, a little chunk of stuff. Whatever that polycrystalline material is. And I don't want you to imagine it as a perfect elastic cube, because those don't exist. Instead, I want you to think about it as warts and all, as a polycrystalline material that has lots of individual little grains. And it is made up of ions on a crystal lattice. And those lattices will have, by definition, thermodynamically have to have defects in the form of vacancies and interstitials. There might be impurities. You can also, if you shear one of these individual grains, one plane of the lattice will move relative to the other plane, and this creates sort of a mismatch in the lattice structure. And so it's actually kind of a negative feature, but we call it a line feature, a dislocation, and it behaves like a line, and these will move in response to applied stress. You can also think about grain boundaries, and those are not perfect planes, but rather they're made up of bumps and asperities, and they have some geometry to them. And at any given time, under different conditions and timescales, all of these kinds of mechanisms might be moving and reacting in response to the stress, but maybe one will dominate. And those will have different signatures that we can talk about. And also, these can be influenced, their motion can be influenced by things like water and melt and the presence of second phases. And what I really want to focus on for the next however many slides is also the frequency of the forcing that you're applying to this chunk of stuff, how that affects its behavior. So now Francis showed some work by Fowle and Jackson, and I think most of Francis's plots were the reverse of this, which probably makes more sense, I suppose, where you've got high frequency on this side and low frequency over there in terms of period. But this is this is how I think. So sorry, all of my plots will be frequency increasing in this direction. So we have way over here on the right side is elastic, that instantaneous response. Way over here we have the long-term quasi-steady state response. And so in terms of materials, if you think about just those two extremes, over here the instantaneous elastic response is really just bonds stretching in between those atoms, versus the viscous response is that those defects are moving, they're moving around, and they're getting into positions that they can't get themselves out of, and so you have permanent deformation. Permanent deformation over here versus in the elastic regime, if you, once you remove the stress, you get it all back, it bounces back. So our two end members are instantaneous, recoverable, long-term, not recoverable. The way you would measure those two end member properties would be, there's lots of ways to measure elastic properties. One good one is to use a non-destructive mean is to use ultrasonic waves. So ultrasonic waves can be, you can send a P wave and an S wave, and from that calculate your various elastic moduli. Versus steady state viscosity, we would, and I'll talk a little bit more about this later when I get to the laboratory experiments, but one way is to take a chunk of stuff and apply a temperature pressure that you want to explore, and you just creep it. You apply a constant stress, and you watch it shorten over time, and you get a curve that looks like this creep curve. So I wanted to introduce the concept, and probably this is familiar to a lot of you, but of these mechanical models that can describe material response. And they're a collection in various ways of springs and dashpots. So a spring represents this elastic behavior versus a dashpot, which represents this slow, viscous behavior that you cannot get back. But all of the exciting stuff that I love to study happens in between these two extremes, and that's the anelastic response, which is time-dependent but fully recoverable deformation. And we do see that in, for instance, in a creep experiment. All the good juicy stuff that you want that covers the whole frequency spectrum can be found in for instance, a creep experiment where, if you can imagine, I teach a lot of sort of high school, college, undergrad level, like intros to rheology, and we do a cheese creep experiment. So we apply a big weight to a chunk of cheese, and we watch it deform over time. It's great because you can get all this same kind of stuff that would take weeks for ice and rock. You can get it in about an hour with cheese. But so what happens is that moment you add a stress, you get an instantaneous just shortening of the sample, and that's just those elastic bonds. And then you've got this evolution where at that first moment it's infinitely high strain rate, if that's the tangent to the line. And that strain rate decreases with time until eventually you get to steady state, assuming you've applied a constant stress. And then if you release the stress, take that weight off, you'll get some rebound. You'll get the sample will actually increase its size, and that is that anelastic part. You're getting all that anelastic part back, but you can't get it all back. All the stuff that you've lost from the steady state, you can't get back. That's permanent strain that's happened to your sample. So that's in the time domain, and there's lots of ways to describe that, but essentially you need a steady state part that describes the viscous response, and an elastic part over here, and then some function to describe that anelastic curve right there. And this is in the time domain. You can do a Laplace transform to get it to the frequency domain. And this describes now the complex compliance of the material. And the complex compliance has a J1 and a J2, the real and imaginary parts of the complex compliance. And those are related to the storage and the loss. So the ability of that little chunk of material to store energy and lose energy. And you can also see here, J1 and J2 also relate to the modulus. And so that this is just a cartoon of attenuation versus and modulus, but as you'll see, it's a pretty good cartoon, and they're usually kind of these mirror images of one another. and certainly have a frequency dependence to the response. So talking about, well, what form of the function do we use here? Don't want to spend too much time on this, but the anelastic response is usually one or more of these parallel units, units of both a dashpot and a spring in parallel. And for instance, you can have a Burger's model, which is just one of these. The group out of ANU often uses an extended Burger's model, which is a bunch of these. They're called Voigt-Kelvin elements. And then there's one that I'm kind of partial to, which is an Andrade model, which uses the integral of those. And you would not have to actually do the Laplace transform yourself. There are tables that provide for these common mechanical models, the kinds of transformation that you need to pull out the J1 and the J2. And I'm going to kind of keep showing this J1 and J2. I believe these are the kinds of values that you're going to need when we start thinking about global properties. And one thing that's important is for how you're describing it mechanically is that, for instance, the form of the Burger's model that has only one of these elements actually gives you this little, when you go from this is the time response versus the frequency response. You'll see at the time response, any one of these mechanical models is a pretty good description of the creep data. But when you transform it, the Burger's model, for instance, puts this little kind of artificial Debye peak in the frequency domain that a lot of materials don't necessarily have, whereas the extended and the Andrade are a little bit more flat. And
Can you explain what Q is a little bit for us? Sorry, you're going a little fast for me.
oh, I'm sorry. Okay, I wasn't sure whether to do mechanical models or the lab experiments. I probably should have done the lab experiments first. But so this is, right, so Francis introduced, mostly he was talking in Q, dissipation factor, and it's the phase lag. The tangent of the phase lag gives you attenuation, which is inverse Q. So quality factor is Q, and then attenuation is inverse Q. And so, right. And so it's just a measure of how dissipative the material is. Sorry about that. And so this is all just a way of this is a way of describing it mathematically, how real materials behave. Because that Maxwell model that just had just an elastic element and just a viscous element doesn't describe the response of a lot of materials. So, and I don't want to try to make it sound like one must use one versus the other, because in this study they found that particularly what we have for experimental data, which should be the black dots, is that both the models pretty much describe the laboratory data pretty equally well. So they just vary in their high and low frequency boundaries, and so that is something we could discuss later. So this is the mechanical or the mathematical way of describing attenuation. But I want, again, like how I view the world is thinking more about that chunk of stuff. So what are the things that cause dissipation? What are the things that cause that anelastic response? And it's the motion of these various defects. And I told you each one would have a signature. And each process might have a distinct length and time scale that manifests in the attenuation, tan delta, that would be attenuation, manifests in the attenuation spectra. So for instance, if you have an atom that's an impurity atom that's sitting in a certain site in the lattice and it basically just moves from a vacancy and then back and vacancy back, that's a very distinct length scale for that to travel. And so if you've got, say, a seismic wave or something like that traveling, it's a very distinct length scale, and how it manifests is as a Debye peak at a certain temperature or a certain frequency. You'll see a peak, and so this is in actually metals, but it kind of just shows you that different types of impurity atoms will manifest. Versus, so that's a Debye peak in the attenuation spectra, versus and I intentionally skipped dislocations because there's a lot we don't really know about dislocations, and I've got a slide or two at the end. But what we do know a lot about is grain boundaries. And if you can imagine now we've got a chunk of stuff and there's got all kinds of grains in there, and you start to shear that material. Immediately the grains, particularly at a nice low stress, the grains are going to want to move past one another. And the moment they do, they get stuck on the triple junctions, and then you get little stress concentrations. And how the system wants to alleviate those stress concentrations is to have mass diffusion along the grain boundaries. And it turns out that so the response we get is a very distributed, this wide, in frequency space, this wide distribution of time scale. And so the thought long ago was that, well, okay, there must be you must have samples that have a distribution of grain sizes. And so that's giving you this broad distribution. But then experiments were so experimentalists a couple decades were really careful to try to really isolate this grain boundary sliding process and this mechanism. They very carefully got very uniform grain size, say 3 micron, and they removed all the extra impurities. They made these very pure samples. They were very careful in fabricating so that they didn't put in any significant number of dislocations. So they were really isolating on a very uniform grain size this one mechanism, and they still saw a wide distribution in the time scale. So they attribute this then to this grain boundary process in response to a stress concentration that diminishes over time. So the more it happens, the more it diminishes. So this diminishing potential creates this broad distribution. So the reason I'm spending probably more time than you wanted to hear about the individual little mechanisms and what that looks like in the spectra is that means we can use laboratory data or response, even observations, to try to understand what mechanism is acting, and that provides how things will scale. Also, when we're trying to scale up to larger bodies. So things we want to look for are the spectra, are there peaks, or are they broad bands? We do all kinds of tricks in the lab to explore grain size and look at grain size dependencies, temperature dependencies, and see how those affect and how we can relate those to steady state processes that are pretty well known. And we can also get some clues from microstructure. So I keep alluding to it, but let's talk about the experiments themselves. So there are several groups that have looked at attenuation in Earth and planetary materials. Group that's done a lot of work out of ANU. They have a rig that basically takes a sample and it does torsion. It goes like this and this, like tickling, very small amplitude tickling in this direction. The work out of my former advisor, Reed Cooper, he was working on in Wisconsin, was again also that same torsional motion. This one uses confining pressure. This one did not. So for my PhD, I was looking instead uniaxially deforming the sample this way. Also at JPL, they were using that. So 2 different ways to study. In this case, they were both used for ice, but you could also use these kinds of commercial rigs for other materials. Regardless of what your configuration is, where you're doing this, ANU was also doing at some point some bending too. Regardless of your configuration, what's happening in the lab is it's very similar to what Francis was talking about with the moon. But what we're doing in the lab is we are applying a sinusoid of stress here, and we're measuring the sinusoid of strain that the sample is responding with, and such that a perfectly elastic material would have no phase lag. But again, we established that does not exist. So any real material that has all of these defects inside will have some lag in the response between the stress and the strain. And we measure that lag. The tangent of that lag is attenuation. And again, that is the ratio of the imaginary to the real component of the complex compliance. Now we also, in the experiment, we measure the ratio of the two amplitudes, because that will give us the moduli. And this is the relaxed modulus, and it changes with frequency. And so I like this little cartoon where we can consider, for instance, this cartoon or this schematic is where it's going from tension to compression, where it's actually was kind of clamped onto a material, a sample, and going in this direction. In all of the experiments that I've shown you, they actually apply some sort of median stress, and about that they oscillate, which is comparable to what these bodies are feeling, where you've got some sort of background tectonic stress about which you've got your periodic tides. Yeah. And so again, this is another rig that I worked on, again uniaxial. This was out of Japan using an organic material as an analog for rock. And we have lots of tricks to try to really explore these behaviors. We can control grain size by having really careful annealing of samples. We can control temperature, and again, thinking about this homologous temperature when we're comparing one mineral type to another mineral type. And we can carefully control impurities. And, you know, I planned to say it earlier, but I just wanted to better late than never, I suppose. But I like to, when I'm talking about these experiments and what's going on microstructurally, is that if you took a metal coat hanger and you bent it back and forth, back and forth, back and forth, and you felt the junction, you would feel heat. And what's happening is that you're turning your mechanical energy into heat, into thermal energy. And that's happening because defects in the coat hanger are frictionally moving back and forth, back and forth. So that's kind of, it's basically the same idea that we're doing here. And that's why I really focus on the individual defects and the kind of spectra and signal that it gives us. And comparison of a lot of different studies. I mean, you might think like, oh, all these different studies are looking at different temporal spaces. We have, some of the rigs have different sensitivities and their strain amplitude resolution. And some are measured in a vacuum, some have confining pressure, some are over here on ice at low temperatures, and some are at ambient pressure. And so there's a lot going. And I told you, geometry, some are turning this way, some are going this way. So some measuring shear modulus versus Young's modulus. And if you looked at just the raw data from a bunch of these studies, I never would show this plot usually because it's not very exciting, it's not very impressive. They're kind of all over the place, and it looks like you're just kind of comparing apples to oranges, which we are, because there are different temperatures, different materials, different testing geometries. But we found that if you normalize each one of these data sets by their Maxwell frequency, so that is for the conditions for each data set, the measured viscosity and the unrelaxed modulus, that you can, that all of the data collapse to a single master curve. So again, that's the, this guy. So again, that's the Maxwell frequency, which is the unrelaxed modulus over the viscosity. And there are different temperatures, so these are both temperature and pressure related. But if you normalize each data set for all of these experimental samples, which are organics, various olivines, single crystals, they all fall to this master curve. And so that's not only powerful in comparing different materials, because what this tells us is there's similitude. So that polycrystalline materials have this same response. And that tells us that the same mechanism is acting, has the same time scale or response. And that, we believe, is that grain boundary sliding, the diffusionally accommodated grain boundary sliding. And again, these were all carefully created to be at very low stress amplitudes, and to have no dislocations in them before, which we could talk about later is how realistic is that. I think to the first order, it's a really good approximation. And so the power, though, of this Maxwell frequency scaling is that it also allows you to think about the conditions in a body and the pressures and temperatures there. So for instance, what we learned when I was working on this with Takei is that when we did this Maxwell frequency scaling, and we're thinking about seismic waves in the Earth, which are at, say, 1 to 100 hertz, and the viscosity and moduli of rock deep in the Earth is pretty high, that actually gives you a range for seismic frequencies that is outside of all of our lab data, which is a little discouraging, and I'll talk a little bit more about things that are happening with that. But when it comes to measuring tidal frequencies, and this is just Europa using a 4 times 10 to the minus 5 frequency, and then scaling by, I used 9 GPa and 10 to the 14th, where one boundary is 10 to the 13th, 10 to the 15th for viscosity, which we can talk about whether that's a good guess. But that puts us deep in the anelastic portion, like way over here where this master curve scaling, it does a pretty good job. Also, I wanted to point out that the gray line here is the Andrade model, which does a nice job of describing, for the most part, the shape of that curve. I also want to talk about that in this normalized frequency scale, the Maxwell time, remember that's that time that divides what we think of as, lower than that time would be purely viscous behavior. Here, that would be 1. And here, this is a Maxwell model, which is just that spring and dashpot only representation of materials. And this is where a Maxwell model would plot on this. So yes, at exactly the Maxwell time, the Maxwell model does an excellent job. But if your system is either higher frequency or lower frequency than the Maxwell model, I don't believe the Maxwell model, of the Maxwell time, I don't believe the Maxwell model does a good job of describing that behavior. So that's something that we want to look out for. And so the power of this is that you can take this, whatever mechanical model you want to choose, you scale it by elasticity and viscosity, which are fairly well known. The required reading that we had to do was a little more pessimistic on what we know about viscosity in various minerals. And yes, in the lab, it is not physically possible for us to measure things at geologic timescales, right? No grad student's going to hang around long enough to do that. So we have to turn some knobs, right? We have to do a few things. We have to go to unrealistically small grain sizes and maybe higher temperatures, higher stresses. So yes, all of our laboratory experiments are outside of the realm of the thing we're trying to describe. However, we're pretty confident. Like we're able to extrapolate those things pretty well. So I wouldn't shy away and say, oh, there's just no way of knowing. Now, I don't have a lot of time, so I just wanted to kind of go through, because I really wanted to sell you on, use this master curve approach and normalize by Maxwell frequency, and let's start there. But there are a couple of problems, and I want to make sure to let you know about the fine print. So the Maxwell frequency scaling just depends on the modulus and the viscosity. They're related to temperature and pressure, so we can use this as a way to scale. Now I've converted it to time scale. So Maxwell time for you, sorry. But one study has a different interpretation of what the grain size dependence, for instance, should be than we do. So if we actually get to the stage this week that we're going over the nitty-gritties of this and actually picking parameters, we can talk more about that. Also, I mentioned that seismic frequencies, what we're dealing with in the Earth, are really high frequencies. It's outside of what we have measured in the lab. And there's this thought that there is a high frequency peak related to elastic grain boundary processes. And that's not really well known. And that's kind of in the world of attenuation, seismic attenuation in Earth. That's the focus right now. But that's way too high frequency for our considerations. So we don't have to worry about that today or this week. Now, I was supposed to mention how melt affects these processes. And so really quickly, we did a study in Japan looking at a partial melt and how it affected that process of grain boundary diffusion. And we found the black dots are samples that had no melt, and then these all had varying degrees of melt. We saw a strong decrease in viscosity, a strong increase in attenuation when you had melt. And the idea being that when you have melt, that creates a superhighway for diffusion around the grain boundaries. And so that seemed to, and this is what happens when we normalized it. So the viscosity caught that, and so the normalization really still worked. This is in contrast to the data out of ANU. They instead also see a specific peak related to, I told you peaks mean a certain length scale, a certain mechanism. So they believe there's something called melt squirt that could happen. So the melt is actually it itself is moving, not just not facilitating diffusion, but the melt is moving. But I believe if you do the calculations and you come up with realistic geometries for this melt, again, that peak would be at high frequencies, much higher than we need to worry about for tidal frequencies. The effect of water on attenuation is not well known, and something that we're still trying to understand now is the effect of dislocation. So if instead of low ambient stress, low stress amplitude, you instead have really high stress, a highly deformed material that might be loaded up with dislocations. At least this study out of ANU showed that the dots are the data from these deformed samples, and the lines are the predicted from the pure undeformed grains. They saw a big increase in attenuation with this prior deformation. But that's how that scales, we're still really not sure, so I don't want to spend too much time on that. And I'll just skip to the end, is that if I really want to drive home, is that material properties are frequency dependent. We should think about the mechanisms, but we can probably do a really good job of approximating that using various mechanical models that we can scale using the Maxwell frequency scaling. So I'll stop there because I've got the red light.